Hi everyone, I'm Dr. Surjit Singh. In this video on Python via examples, we shall talk about sorting of a linked list. Let us begin. In this session, we will develop the sort method of a linked list class. We will set up the move node method to change the position of the nodes. We may also require moving the node to the head or from the head. We will also require the findMin method to find node in a given range that has minimum data. We know that swapping of the data attributes of the nodes is slower than swapping of their next attributes. So we will use swapping of the next attributes while sorting a linked list. In a previous video, we used the node class to define a linked list class. We use a list of numbers to create a linked list object. We have already defined its print method to print it. We will now develop modules required for sorting the list. In sorting, nodes change their positions within the linked list. For this, we will now write method to move nodes within the linked list. Let us consider node 3 as an example. We will move it so that it becomes the child of node 2. It means that we move node 3 between 2 and 4. For this, we require the parent of node 3. We will let the parent to point to the child of node 3. With this, node 3 becomes free. We can now make it to become the child of node 2. In the next two steps, 2 points to 3 and 3 points to 4. Node movement becomes complete. 6 was the old parent of 3, while 2 has become its new parent. We need these two parents to carry out these movements of the next attributes of the nodes. Let us now write the Python method for moving the child of the old parent to become the child of new parent. N1 is the node next to head. We will make it the new parent. N2 is 3 nodes further ahead of N1. This is the old parent of the node that we will move. To be sure, let us print their data attributes. Old parent is 6 and new parent is 2. We now pass these two parent nodes to the move node method. N2 is the old parent and N1 is the new parent in the move node method. Node that we want to move is the child of old parent. So we let next of old parent to point to the child of node. Node is now free and we can make it the child of new parent. However, before doing that, we must save the existing child of new parent. We save it in variable child. New parent is now made parent of the node and node is made the parent of the child node. Move node method ends. We confirm it by printing the latest arrangement of the list. We have successfully detached node 3 from its old parent and made it the child of the new parent. One of the two special cases of move node is in which we move a node to the head position of the list. It means that 3 will be the new head and 1 will be the child of 3. Once again, we save the address of node 6 in N2, print it for verification, and call it the old parent in the move node method. But node at the head does not have the parent, so we pass none to the new parent. First two statements of move node work in the same way. Node is the child of old parent. We remove it from the chain. Let us now make room for a few more statements in the move node method. Next two statements work only if new parent is present, so we put them in the if block. In the present case, new parent is none, so we execute the else part. Existing head is to be made the child of node 3, so we save it as child. We can now make node as the new head. Common statement to both the blocks links node with the child. Move node method ends. Print method now gives the desired output. 3 is the head and 1 is its child. Another special case of move node is in which we move the node located at the head to a new position. In this example, we are moving node 1 between 6 and 3. Node 2 will become the new head of the list. Node at the head does not have a parent, so we pass none to the old parent. Node 6 will become the new parent of node 1. Let us make the required changes in the move node method. These two statements are needed if old parent is present. Otherwise, we save head in node and move head to 2. Rest of the execution is same and we come out of the move node method. Print method confirms this movement of the node at the head. First step in selection sort is to find the node with minimum data within a range of nodes. Actually, we will return the parent of the node with minimum data. We identify the search range of nodes by identifying the parent of the starting node of the range. In this example, we set node 1 to be the parent of the starting node, so search range is from node 4 to the end of the list. We pass the parent node of range, that is node 1, to the find minimum method and save it as parent. The method returns the parent of the node that has minimum data out of all the nodes in this range. Searching range starts with the node that is next to the parent. We save it as initial value of the variable node. If we want to scan the entire linked list, we pass none to the parent, which invokes the else part, and we fix the starting node to be the one at the head. In that case, range of nodes starts from the beginning of the linked list. We come back to our selected range in which starting node is node 4. We save the data of the current node as min data and its parent as the min parent. Starting with node 4, we scan all the nodes in a while loop. Whenever the data value of the node is less than the saved value in min data, we revise both min data and min parent. We then move parent to node and node to the next position. In the next iteration again, the if statement is false. We move parent to node and node to next position. One more iteration of the loop goes the same way. Now that node data is 3, which is less than min data, the if statement is true. So we save 3 in min data and parent in min parent. Like in every iteration, parent moves to node and node moves to 7 this time. In the last iteration, parent becomes 7 and node becomes none. With this, the loop terminates and we return the min parent. The method ends and we save min parent in n. It is the parent of the node that has minimum data. Printing confirms that it is node 6, that is the parent of node 3, which has the minimum data out of the given range of nodes. Like before, if min data is at the head of the linked list, the returned node n will be none. We have developed all the methods required for sorting a linked list. In this section, we will write method for the selection sort. As discussed earlier, we will be moving next attributes of the nodes to change their positions. Let us take the example of the given linked list for sorting it. If linked list is empty, we do nothing. For other lists, the first step is to find the minimum data of all the nodes which will become the new head of the linked list. For this, we pass none as the parameter to find min method and therefore Starting with the head, we scan all the nodes using the find-min method. In the range of nodes, minimum data is found to be the node 1. Its parent node is saved in old parent. It is not none, so node 1 is not the parent node. Move node method makes it the new head by moving the pointers as shown here. Let us simplify the appearance of the linked list without disturbing the next attributes in the memory of the computer. Now that head gets the lowest data, we will fix the order of the remaining nodes in a loop. We start with the range of the nodes that start with the node next to the head. It means head will be the new parent for that node. In a loop, we will cover all the nodes in the range. A node can be a parent as long as another node is present next to it, so the loop will terminate when it is the last node. Find-min scans all the nodes that follow the new parent. It finds the parent of the node that has the smallest data, which is the old parent of the node that we will move. Smallest node is found to be node 2. The new and old parents are the same. Move node does nothing and node 2 remains at its original position. New parent moves ahead for the next iteration. This time we find the old parent of the smallest node in the residual range. We then detach it from the old parent and join it with the new parent. Insertion of node 3 is complete. Linked list nodes are seldom placed in adjacent memories. In fact, they are often scattered throughout the memory. The movements that we are now showing are just for the better visualization of the chain of nodes. Nodes are actually staying in the memories wherever they are. Node 3 is now present next to the new parent. For the next iteration, it becomes the new parent. Loop continues. Till all the nodes are sorted. Next attribute of new parent has now become none, so the loop terminates and the sort method ends. Print confirms that the sorting is complete. In this session, our aim was to write a sort function for a linked list. For testing, we printed the list before and after sorting. For this, we wrote the move node method. Moving a node to the head is a special case in move node. Another special case is of moving the node at the head of the list. Next, we wrote method to find parent of the node that has minimum data within a range of nodes. First step in the sort method is to move the smallest node at the head. After that, in a loop, we processed the remaining nodes and in each iteration brought the smallest node at the beginning of the range. Range size is reduced by 1 in each iteration till the sorting is complete. I hope you enjoyed the video. Please feel free to ask for further clarifications on my email address given below. I'm looking forward for your comments. Please stay tuned for more.